Hey, good afternoon, class, and welcome back. These polynomial functions. So, based upon what you've observed so far, write an equation of a function that has the following features. Produce a different function for each part and confirm your answers with graphs. What I'd like you to do is just take a few minutes to, first I'd like you to pause this, then take a few minutes to answer 4 or 5 of these. See what you can come up with for equations that satisfy the given information. So write a function equation for a function that has only one vertical asymptote at x equaling 3. Now there's going to be a variety of different answers, and we will talk about what your answers may look like compared to what I have. So check back here after answering 4 or 5 of these. So please pause this now. Alright, welcome back to problem 4-68. In part A, you want only one vertical asymptote at x equaling 3. Well, that means x minus 3 needs to be in your denominator, because if x minus 3 is the factor in your denominator and you set that equal to 0, then x comes out to be 3. And when x is 3, you end up with your denominator equaling 0, which makes your graph undefined. In part B, and then by the way, in f of x, you could have a variety of different equations. Maybe in this in part A, you have 2 over x minus 3. Or maybe you've got 5 over x minus 3. Or maybe you have x plus 7 over x minus 3. All of those work, provided your denominator has an x minus 3 in it. Only a whole, for part B now, only a whole at x equaling 3. Well, in order to have a whole, that means the factor of x minus 3 needs to be in the denominator as well as the numerator so that they cancel. And you are left with an equation of just x plus 1. In part C, you're going to have wholes at x equaling a negative 1 and x equaling 1. Again, that tells us that I need 2 factors that occur in the numerator as well as in the denominator. Now you can see the problem that I have written over here. I have the x minus 1 and the x plus 1 in the numerator, but in the denominator I got x squared minus 1. Well, that's because you can factor the denominator, and so h of x equals 3 times x minus 1 times x plus 1 all over this. Here's the difference of 2 perfect squares, so I have x minus 1 times x plus 1, and those factors, x minus 1's cancel, the x plus 1's cancel. Part D, I need a whole at x equaling 4 with a graph of y equaling x plus 6. That means after I reduce my whole, I need to have the equation of x plus 6 left over. So my equation is going to be x plus 6 times x minus 4 all over x minus 4. Those cancel, and I'm left with x plus 6. In part E, I need a whole at x equaling 2 and an asymptote at x equaling a negative 3. That means in my denominator, I need both an x minus 2 factor and an x plus 3 factor. The x minus 2 is going to create the whole, and the x plus 3 is going to create the asymptote. In my numerator, I just need a factor of x minus 2, so that will cancel with the x minus 2. Now this is getting to be a little bit messy, so I want to undo some of this yellow writing so that things clean up just a little bit. Oops. Now let's move on to part E. In part E, it says, or excuse me, in part F, the last one, a hole at x equaling a negative 2 in the graph of y equaling x squared minus 9. This x equaling a negative 2 is going to be a factor of x plus 2 in the denominator and x plus 2 in the numerator. They cancel, and I'm left with an equation of x squared minus 9. Now, here's one recommendation I would have to help understand this concept of a hole a little bit better. Take some time to go meet with your teacher during their office hours and talk to them about how to use your calculator to explore these functions. Now, we're going to be doing a lot more of that in the next few problems. A lot of my answers are already going to be pre-made, and so there will be graphs that you can analyze, but that's still not going to be the same as doing this on your own calculator and trying to figure out how do I see a hole, or where is a hole in this particular function. So just a little heads up, go talk to your teacher during office hours about how to examine these using your calculator. Now let's move on to the next slide. We're going to analyze these functions. Now when we say analyze a function, what we're asking you to do is to look very closely at the domain range, your x-intercepts, your y-intercepts, horizontal or slant asymptote, vertical asymptote, any holes, and what the end behavior. So let's start by analyzing a of x equaling 1 over x squared minus x minus 12. We always start out by writing this in factored form. That's going to help us analyze and determine holes and vertical asymptotes. So a of x equals 1 over x minus 4 times x plus 3. My domain then is going to be all reals except what gives us a 0 in the denominator. That's what you're looking for. Where is the denominator equal to 0? And we have to exclude that from our domain. So when x equals 4 and when x equals a negative 3, I'm going to get 0 in my denominator. So my domain is going to be all reals except negative 3 and 4. Now the range is going to be all reals except y is not going to be able to equal 0. Because if you analyze this graph or analyze the function, you'll see that the output y values can't be 0. Now, in order to do that from a graphical or from an equation standpoint, if I have a of x equaling 1 over x squared minus x minus 12, and I start thinking about, okay, what are my output values going to be? What can and can't come out of this? Well, in order for 0 to be an output value, that means my numerator has to be 0, because 0 divided by anything is 0. But my numerator is 1. My numerator will never be 0. Therefore, this function can never equal 0. Or in terms of my range cannot be 0. Now for x-intercepts. This is going to tie in closely with my answer from the range, because an x-intercept is some x value, comma, 0 for y. Well, we just stated up above that y cannot be 0, because the numerator cannot equal 0. Therefore, what x value is going to give me an output of 0? That's what this is asking. If my equation is 1 over x squared minus x minus 12, and I need to get an output of 0, I can't do that. Therefore, there are no x-intercepts. Y-intercepts occur when x is 0. And so we're going to plug 0 in for x and see what we get for an output. So I'm going to take a of x equaling 1 over 0 squared minus 0 minus 12. Well, 0 squared is 0, minus 0 is 0, minus 12 is negative 12. Therefore, my y-intercept is 0, negative 1/12. Horizontal or slant asymptote. Well, if you analyze the graph, you'll see that the graph cannot have an output of 0. Therefore, the graph is approaching y equaling 0. Another way to look at that is, in one of the previous videos, I talked about the most influential term in the numerator and most influential term in the denominator. So if I take the function a of x, and I take a look at my numerator, the only value I have there is 1. If I take a look at the denominator, the most influential term in the denominator is x squared. And as x gets very, very large, it's going to tie into end behavior. As x goes to infinity, what's happening to a of x or y? Well, my denominator is getting larger and larger and larger, but then this overall value is going to get smaller and smaller and closer to 0. So that's what leads us to know that I have this horizontal asymptote at y equaling 0. Later on you'll hear me talking about it. Since the degree of the denominator is larger than the degree of the numerator, the horizontal asymptote has to be 0. Now what about vertical asymptotes? Well, that comes back to our domain. So horizontal asymptote, let's talk about this quickly. Horizontal asymptote, that tied to your range. Vertical asymptote, that's going to tie into your domain. The vertical asymptotes, x minus, or x equaling negative 3 and x equaling 4, because that's what x can't be. Holes. We don't have any holes here because we didn't have any factors reduce. Holes, again, will tie into the concept of your restrictions on your domain. End behavior. I already started hinting at that. My end behavior is, as x gets very, very large, y is going to go to 0 because my denominator is getting very, very large for the most influential term, and therefore the overall value is going to get closer and closer to 0. And if I go to a negative infinity, well, then my denominator is going to become a very large negative number, which 1 over larger and larger negative numbers also then goes to 0. Now what I'd like you to do is take a minute, think about some of the things we just did, make a graph of a of x, and see how these items appear in your graph. You can start with a standard viewing window for a of x, but then you may want to adjust it so that you zoom in just a little bit, and you really only need to go x can be between 5 and a negative 5, and the same thing with y. So if you want to make a new viewing window, all you need to do is go from a negative 5 to 5 for both x and y. Take a minute, review some of these things, and then come back and let's take a look at part B. So let's take a look at part B. We'll actually take a look at B, C, and D, and then maybe try a couple of them at the end. So in part B, here's my equation, x minus 4 over x squared minus x minus 12. First thing you want to do is you want to write it in factored form. And what I notice is that the x minus 4's can cancel. That's what's going to create a hole when factors cancel. And my reduced form is now 1 over x plus 3. So my domain is going to be all reals except for what x can't be. Now you've done a lot of work with restricting your domain before. So in the original equation, when I had it in factored form, I had in my denominator x minus 4 and x plus 3. Therefore my domain is all reals except x equaling 4 and negative 3. The range, I know we talked about the range in part A. Please don't worry about finding the range in these other problems or these other functions. Now vertical asymptotes, horizontal asymptotes or slant asymptotes, holes, those will be the next couple things we tackle. A vertical asymptote, since x minus 4 canceled, that's not going to create a vertical asymptote. Only what the factor that's left over in the denominator will create my vertical asymptote of x equaling a negative 3, because I can't have 0 in the denominator. The graph of this has a horizontal asymptote at y equaling 0, because the graph, if you take a look down below, and you can type this in your calculator, this keeps getting closer and closer to 0 from a positive side and from this negative side. So I have a horizontal asymptote at y equaling 0. Another way to look at that is take a look at the most influential term in your numerator and most influential term in your denominator. And this is going to help you determine your end behavior. So we're actually going to jump down to that since we're talking about the horizontal asymptote. As x gets very large, the only part of this function for b of x that really matters is that those most influential terms in the numerator and denominator. So I get 1 over x. Well, as x goes to positive infinity, what is my output going to go to? It's going to get closer and closer to 0, because x is going to get very large in the denominator, making the overall value closer and closer to 0. And as x goes to negative infinity, this is still going to get closer and closer to 0, because my denominator is going to become a very large negative number, making this overall value become closer and closer to 0. So that's why we have a horizontal asymptote at y equaling 0. This graph from both the positive side and from a negative side is going to get closer and closer to 0. Now, that factor that we canceled, that x minus 4 over x minus 4, that's going to create a hole where x takes on the value of 4. And we then have to find the corresponding y value. Well, in order to find the corresponding y value, I need to take 4 and plug it into that simplified equation. So if b of x is equal to 1 over x plus 3, and if I plug 4 in there, I get an output of 1/7. So I have a hole at 4, 1/7. What about x-intercepts? Well, x-intercepts occur when the y value is 0. So I need to find an x value when y is 0. But if I take 0 and I set that equal to 1 over x plus 3, I cannot get an output of 0. Therefore, there is no x-intercept. Now for a y-intercept, that occurs when x is 0. So I'm going to take the equation, plug 0 in it, or plug 0 in for x, and I get an output of 1/3. So my overall graph, if I was to try to sketch this using the information up above, I have a y-intercept of 0, 1/3. I have a hole at 4, 1/7, which I'm going to have to be a little bit more cognizant of in the future of drawing. So I've got this hole right here at 4, 1/7. I have a vertical asymptote at a -3, horizontal asymptote at 0, and the rest of this is that curve or hyperbolic shape that passes through 0, 1/3. I've got a hole there, and I keep getting closer and closer to the x-axis. And the same thing from this negative side. Now with this one, I'm going to write less, so hopefully you can follow along. That way things might stay a little bit more clear. I'm starting out with c of x equaling x squared minus 16 over x squared minus x plus 12. And I need to write that into factored form. So my numerator factors into x minus 4 times x plus 4. The denominator factors into x minus 4 times x plus 3. Again, I'm going to create a hole because I have an x minus 4 factor in the numerator cancel with an x minus 4 in the denominator. That leaves me with the polynomial of, the rational expression of x plus 4 over x plus 3. My domain restrictions come from the original factored form. So my domain is going to be all reals except 4 and -3, because that's what makes the denominator equal to 0. And we can't have 0 in the denominator. Do not worry about finding the range. Vertical asymptotes and holes. Those come from restrictions on your domain. So as I look at my simplified factored form, I see that x can't be a -3. Therefore, since that factor remains in this factored form, it gives rise to a vertical asymptote of x equaling a -3. The factor that I crossed off gives rise to the hole. So my x is going to be 4. The output, the y value for the hole, then comes from plugging 4 into the simplified factored form. If I plug 4 in there, I get 4 plus 4, which is 8, and 4 plus 3, which is 7. So my hole is going to be at 4, 8/7. Horizontal asymptote. Now, these can be found by performing long division. And I didn't talk about it on the last problem. I tried to give you more of a general concept. But if I take my simplified rational expression, x plus 4 over x plus 3, and I perform my polydoku or polynomial division, I end up with x plus 3 going into x plus 4 one time. So then 1 times x is x, and then 1 times 3 is 3. I have a remainder left over of 1. So if I take and write this c of x out, I've taken x plus 4 and divided that by x plus 3, and that goes in or x plus 3 goes in there one time, that's this one right here, and that remainder then is 1 over x plus 3. The number of times the denominator goes into the numerator, that is your horizontal asymptote. That's just another way to look at that most influential term piece. Now for your x-intercept occurs when y is 0, so put 0 in for y and solve. Well, in order for this rational expression to equal 0, the numerator has to equal 0. So x plus 4 equals 0, solve for x comes out to be a negative 4. To find the y-intercept, the y-intercept occurs when x is 0. So I'm going to put 0 in for x, and my output then becomes 4/3. End behavior, your end behavior is your horizontal asymptote. So as x gets very large, as x goes to a positive infinity, and as x goes to a negative infinity, this graph is going to approach the horizontal asymptote of y equaling 1. Take your calculator, sketch a graph, and as you sketch that graph, apply everything that we have up here. Start by marking any x or y intercepts. So I'm going to put a y-intercept of 0 4/3, so we have a dot there. I have an x-intercept of a negative 4 0. I have a hole that I'm going to mark. That's at 4 8/7. That's right there. Then a vertical asymptote at x equaling a negative 3, horizontal asymptote at y equaling 1, and then sketch your graph. I will do one more of these, especially trying to emphasize this polynomial division. Okay, let's take d of x equaling x squared minus x all over x plus 3. If I take the equation and write it in factored form, I'm going to factor out an x in the numerator. So I have x times x minus 1 all over x plus 3. My domain, taking a look at my denominator, is all reals except a negative 3. Now I'm going to go right from domain into vertical asymptote and holes, because that's tied to your domain restrictions. I only have the one restriction, therefore my vertical asymptote is x equaling a negative 3. There is no hole. My polynomial division. Now if I take x squared minus x divided by x plus 3, that will help me determine any horizontal or slant asymptotes. So using that polynomial division, or Polydoku division, I'm going to take x plus 3, divide that into x squared minus x, and what I get for a quotient is x minus 4. Therefore, x plus 3 divides into x squared minus x and x minus 4 times, with a remainder of 12, so plus 12 over x plus 3. This here is my slant asymptote. X-intercepts occur when y is 0, so put 0 in for y, and analyze your numerator. My numerator then, x squared minus x, set that equal to 0, and solve for x. I use factoring, so x comes out to equal 0 and x comes out to be 1. So now my x-intercepts, 0 0 and 1 0. Y-intercept occurs when x is 0. So put 0 in for x, and your output comes out to be 0. end behavior. Since this graph has a slant asymptote, that means as x gets larger, y is going to approach that slant asymptote, but that slant asymptote is increasing. Therefore, y is going to go to a positive infinity, and we'll take a look at this on the graph in just a minute. And as x goes to a negative infinity, y is going to approach that slant asymptote, but since it's getting smaller in the negative direction, y is going to go to a negative infinity. So if I slide this up and actually sketch my graph or take a look at it on my calculator, I've got my vertical asymptote drawn. I've sketched the slant asymptote. I've also plotted my x-intercepts, y-intercept, and sketched the graph. As x goes to positive infinity, as x is going to positive infinity, as x is getting larger and larger, my y values keep getting larger and larger. They're approaching the slant asymptote, but that y value is getting further away from the x-axis, so it is getting larger. It's going to a positive infinity. And as x goes to a negative infinity, my y value keeps getting closer and closer to that slant asymptote, but that overall distance from the x-axis keeps increasing. It's becoming more negative. It's coming further below the x-axis. What I'd like you to do is pause this and then go onto the slides and attempt to find the factored form, the domain. You don't have to worry about the range, your x-intercepts, y-intercepts, any horizontal or slant asymptotes, any vertical asymptotes or holes, and then determine the end behavior for both part E. Then come back and check your answers. So here are your answers for part E. I'm not going to go through it because of the time of this video. You can read through this. I highly recommend getting a group of students together, hosting your own Zoom meeting, talking about your solutions, how you came up with this, or FaceTime each other. I'll take a minute, pause this, try to come up with your factored form, domain, skip the range part, your x-intercepts, y-intercept, slant or horizontal asymptotes, vertical asymptotes, holes, and behavior. And then come back and check your answers. Okay, welcome back. I do want to talk just briefly about this one. You can take a look at your factored form, your domain, your range, which you can ignore. Oops, hang on. X-intercepts, y-intercepts. So take a minute or two, pause this, look through this, but then I want to talk about that horizontal or slant asymptote. Okay, hopefully you checked your work. As you look at these rational expressions and you're trying to determine what the horizontal or slant asymptote is, if the degree of the numerator is larger than the degree of the denominator, then you're going to end up with a slant asymptote, because the denominator is going to go into that numerator x number of times. And I should probably clarify, provided that the degree of the numerator is just one value larger than the degree of the denominator, you'll have a slant asymptote. And so if you were to take and just analyze the most influential terms, you'll see that x would go into x squared x number of times. So you're going to end up with some type of linear slant asymptote. And doing the division, x plus 3 divided into x squared plus 4x minus 12, you end up with the x plus 1. That becomes your slant asymptote, and so you could graph that line, making it dashed, graph your vertical asymptote, plot your x-intercepts, plot your y-intercept, there is no hole, and you can sketch your graph. Now this is the one problem that I referred to you earlier in the problem. I kind of made mention of seeing your teacher during office hours so that you can talk to them about how to find holes, asymptotes, things like that on the calculator, because some calculators may not show asymptotes or holes correctly. So you may need to pay particularly close attention to what your calculator is capable of. Sometimes your teacher can help you with that. We are going to skip this page for now. It's going to be kind of covered on the next page. As we take a look at the graphs that we created, in problem 69 we had A, B, C, D, E, and F. Things that we noticed is there were quite a few that had some point discontinuity. In other words, they had a hole. And that point discontinuity occurs when the function has a giant 1 when written in factored form, so that that factor reduces. That can be seen in B, C, and E from problem 69. All right, vertical asymptotes occur when at least one factor remains in the denominator in simplified form. So you have one to your vertical asymptotes. Again, those vertical asymptotes are tied directly to your domain restrictions. Horizontal asymptotes, now this is going to occur when the polynomial in the numerator has a degree equal to or 1 less than the degree of the denominator. If the degree of the denominator equals the degree of the numerator, you can use polynomial division to find that horizontal asymptote. And that horizontal asymptote will be some constant. So y will equal some constant k. If the degree of the denominator is greater than the degree of the numerator, then that horizontal asymptote will always be 0. Now, for slant asymptotes occur when the polynomial in the numerator is 1 degree greater than the polynomial in the denominator. That occurred in problems D and F. And that's where you're going to want to use polynomial division or Polydoku division to find that equation. There's definitely a few more things we could be going through. There's another example over here, question 4-72. A lot of the concepts that are emphasized in this particular problem have been covered in previous problems. But this might be one of those where talk to your teacher during office hours about some of these solutions. I hope you enjoyed this video, and remember, talk with your teachers. Please, those of you who are getting the daily work done, the homework assignments, keep doing that. Keep doing those exit slips. There's a lot of good concepts being evaluated in the exit slips, and those exit slips can give you some immediate feedback on whether you're understanding the concepts. And if you're not, then please talk to your teacher during office hours. Wishing you all the best. Take care, be safe, and be well.